Welcome to Module 5 of the Meggitt Sensing Systems Industrial Vibration Training course, Diagnostics Part B. In this module, we will cover how to diagnose bearing problems, looseness, and resonance. Generally speaking, there are two types of bearings: journal bearings, sometimes called sleeve or babbitt bearings, and roller element bearings, which include different types like deep groove ball bearings, cylindrical roller bearings, spherical roller bearings, taper roller bearings, thrust bearings, and others. With journal bearings, the shaft rides on a film of lubrication in a journal. As the shaft rotates, a lubrication wedge is formed between the shaft and the journal. For this type of bearing, the best type of monitoring is proximity probes. To detect wear in journal bearings, it is best to use proximity probes to determine the actual shaft movement. When wear is severe, multiple harmonics of rotational speed will be present in a vibration spectrum, which is often accompanied with elevated noise floor. Excessive clearances will exhibit a very similar vibration response. Oil whirl occurs when the lubrication inside of a journal bearing whirls enough to cause shaft instability. This is indicated by the presence of the oil whirl frequency, which is typically between 0.4 and 0.5 times rotational speed. Oil whirl is considered severe when the levels exceed 40 to 50% of the clearances. Oil whip occurs when the oil whirl frequency coincides with the system's natural frequency. The system natural frequency amplifies the effects of the oil whirl. When this occurs, an increase in speed will often not correct the problem. There are many different types of roller element bearings that include deep groove ball bearings, cylindrical roller bearings, spherical roller bearings, thrust bearings, and others. Each type of bearing will have unique characteristics, but they will all share some common rules of thumb. The actual bearing defect frequencies are based off the geometry of the bearing and the speed at which it rotates. A roller element bearing has several components. The major components are the outer race, the inner race, the roller elements, and the cage that holds the roller elements together. These components are what create our bearing defect frequencies. Ball pass frequency outer race, or BPFO, is created when a roller element passes a defect that is present on the outer race. Ball pass frequency inner race, or BPFI, is created when a roller element passes a defect that is present on the inner race. Ball spin frequency is created when damage to the roller elements occurs and is usually a result of other damage. Cage frequency will typically show up as a modulating frequency, creating sidebands around ball pass frequency outer race and ball pass frequency inner race frequencies. If we do not know the actual defect frequencies for a bearing, we can use some rules of thumb to roughly calculate them. If we know the number of roller elements in a bearing, we can multiply that by the rotational speed. This number can then be split into two parts, 60% of the number representing the rough inner race frequency and 40% of the number representing the rough outer race frequency. So if we have a 10 roller element bearing rotating at 1800 RPM, our inner race frequency will be roughly 10,800 CPM, and our outer race frequency will be roughly 7,200 CPM. The outer race frequency ratio, when added to the inner race frequency ratio, must add up to the total number of roller elements in the bearing. The actual calculated frequencies are available from the bearing manufacturers. Bearing defects will typically manifest in what is called the load zone of a bearing. When collecting vibration data, it is best to collect the measurement as close to the load zone as possible. Bearing defect frequencies can attenuate very quickly as they propagate away from the point of initiation. Ball pass frequency outer race frequencies tend to be the highest in amplitude because they are typically closer to the sensor and thus less attenuation occurs. There are 4 recognized stages of bearing failures. In stage 1, the defects are below the bearing surface and will not be visible to the naked eye when disassembled. When a bearing reaches stage 1 failure, the energy in the very high frequency ranges will increase, but they may not be detectable with vibration data collection equipment. When a bearing enters stage 2 bearing failure, they are still primarily subsurface defects. The vibration at the very high frequencies from stage 1 will continue to increase. Additionally, the bearing natural frequency may become evident. The defects will not likely be visible to the naked eye when disassembled, but they are likely visible under magnification. In stage 3 of a bearing failure, the defects have now risen to the surface of the race and should be visible to the naked eye if disassembled. Bearing defect frequencies will now become evident in the spectrum, and as wear progresses, sidebanding can occur around these frequencies. The sidebanding is typically spaced at cage frequency for outer race defects and rotational speed for inner race defects. Significant impacting should become evident in the time waveform. In stage 4 of bearing failure, the surface defects are now significant and can easily be seen if disassembled. In this stage, bearing defect frequencies can diminish as the bearing approaches failure. Harmonics of rotational speed can become evident and the noise floor will increase. High-frequency measurements can appear to diminish and then become very high just before functional failure. There are 3 recognized types of looseness: structural looseness, or type A, mounting looseness, or type B, and internal looseness, or type C. Structural looseness will exhibit high levels of 1 times rotational speed vibration that will dominate the spectrum. There can be multiples of running speed, but they will be at much lower amplitudes. The loose component can be identified with phase. The phase will shift 180 degrees across the loose component. Mounting looseness will exhibit 1 or more harmonics of rotational speed, and 2 times rotational speed can dominate the spectrum. The amplitudes due to this type of looseness can be very erratic, and the phase measurements will often be unstable. Internal looseness will exhibit several harmonics of rotational speed and tends to be directional and primarily evident in the radial direction. The phase measurements can be very unstable. When this type of looseness is severe, it is common to see partial harmonics such as 1/3, 1/2, and 1.5 times harmonics. Before we discuss resonance, we should first become familiar with a few terms. Natural frequency. This is the frequency of free vibration of a system. The frequency at which an undampened system with a single degree of freedom will oscillate upon excitation. Resonance is a condition that occurs when the forcing frequency coincides with the natural frequency of a system. A forcing frequency can be unbalance, misalignment, looseness, or other things. Critical frequency is a special instance of resonance in which natural frequencies are excited by the rotational speed of the system. And torsional resonance is a frequency at which angular vibration will occur. Think of it as a twisting vibration. This is not detectable with traditional means of vibration analysis. Everything has natural frequencies. A good example of a natural frequency is a tuning fork or a guitar string. When excited, they give off a vibration. In an excited state, vibrations of 10 times to 100 times the induced stress may be created. Generally, only lower natural frequencies are of concern when dealing with vibration. Natural frequencies are very directional in nature, and they are not a defect. Critical frequency is a resonance at which the forcing frequency is the running speed of the equipment. This can vary because the natural frequencies are dependent on stiffness and mass. Changes in machine speed and load can affect this stiffness and mass. Testing is more challenging. Typically, you will need a combination of impact testing and startup coast down. Machines should be designed not to operate within 20% plus or minus of the critical speed. A mode shape is the deflected shape of a structure when a particular critical frequency is excited. When we pass through the first critical, the center of our roll is at the point of maximum deflection. This is an antinode. When we pass through the second critical, the center point is of least deflection, which is called a node. When we pass through our third critical, we now have nodes at each end with 2 additional nodes about 1/3 away from the ends. Characteristics of resonance and critical frequency are significant vibration amplitude at a specific frequency, This high amplitude is very directional. Resonant amplitude is 4 to 20 times higher than that of the same frequency in other directions. High vibration exists during a particular operational condition, such as certain speed or a certain load, a lack of response to balancing, broken machine structure or welds, and a 180-degree phase shift through resonant frequency. There are many sources that can excite a resonance, including running speed, unbalance, misalignment, gear mesh, vane pass, and others. There are several methods we can use to test for resonances. Impact testing can provide the frequency of the resonance, and if a dual channel test is performed with a modal hammer, it can provide phase information. A startup or coast down can provide both the frequency and phase information, but requires the use of a tachometer. Operation deflection shape testing is based on amplitude and phase measurements and can help provide a clearer understanding of a system response to a particular frequency. Strain gauges and specialized testing usually require an extensive setup, experience access issues, and require specialized equipment. To perform an impact test, you will need a single channel or a dual channel vibration instrument. An instrument with pre-trigger and negative averaging capabilities is desirable. You will also need an impact source such as a dead blow hammer, rubber mallet, 2x4, or a modal hammer. Keep in mind that different impact sources will excite different ranges of frequencies. Harder sources will excite higher frequencies, and softer sources will excite lower frequencies. This type of measurement will provide the frequency of a resonance, and if performed with a modal hammer using a dual channel system, will provide phase information. When interpreting the results of an impact test, the amount of ring down is an indication of the amount of damping. A lightly dampened system will provide a long ring down. It is important to ensure that the signal approaches zero by the end of the time record for this test. The derived spectrum can give us a rough idea of the frequency of a resonance and the amount of amplification. Sharp peaks are an indication of higher amplification. To perform a coast down test, you will need a single or dual channel vibration instrument that has a coast down capability and a tachometer input. The ability to display Bode or polar plots is desirable. This type of measurement will provide frequency and amplitude information as well as phase and speed information. This measurement can only identify resonances or criticals that can be excited by running speed. This excludes resonances that occur at multiples of running speed or are excited by a mechanical influence such as gear mesh. Here is an example of a Bode plot where we have a resonant frequency from 826 CPM to 1596 CPM. This is evident from an increase in the vibration in the upper plot. This increase must be in conjunction with a 180-degree phase shift from the beginning to the end of the resonance range. You will notice that the highest amplitudes are detected when the phase shift is at 90 degrees. Polar plots are a graphical representation of amplitude and phase. When a resonance occurs, it will cause a loop in the data. Polar plots cannot determine at what speed the resonance occurs. To perform operational deflection shape testing, you will need a single or dual channel vibration instrument that has the ability to measure phase. It must have a tachometer input, and the ability to store phase measurements is highly desirable. You will also need a method to visualize your results, such as a graph paper or an ODS software package. To perform an ODS, you will need to divide the component being tested into several evenly spaced measurement locations. There must be enough locations to extrapolate a mode shape. An ODS can be performed on a running machine to identify the machine's response to a particular frequency, but can also be done with the use of an external vibration source. This is very useful when testing components such as a shaft. In this example, the base was excited with an external source. The frequency of the excitation was 1180 CPM and was in a non-resonant range. The amplitude of the input was 0.12 inches per second. In general, the measurements decreased in amplitude the farther away from the input source we measured. You will notice that all of the response measurements are less in amplitude than the source vibration. In this example, we excited the base with an external source. but this time we excited it at 1780 CPM, which is within a resonance range. The input amplitude was 0.36 inches per second. You'll notice two things that are important. First, all the vibration measurements are of a higher amplitude than the input vibration. And second, the measurement amplitudes vary in magnitude, similar to the first mode shape. The shape combined with the amplification clearly illustrates a resonance condition. There are two ways to correct a resonance. We can change the stiffness or we can change the mass. We can increase the stiffness of a system by adding additional supports. This will effectively raise the natural frequency of the system. This change is often enough to eliminate the amplification that is occurring. In this example, on the left, our resonant frequencies are 1320 CPM and 1920 CPM. When we change the stiffness by adding supports, these resonant frequencies shift to 1440 CPM and 2040 CPM as illustrated in the example on the right. We can also change the resonant frequency by changing the mass or by adding and removing weight from the system. Adding weight lowers the natural frequency of the system. Often the amount of weight or mass required to achieve the shift needed is very large and often not practical. In the example on the left, our resonant frequencies are 3720 CPM and 7950 CPM. By adding mass to the system, these frequencies shift to 3600 CPM and 7680 CPM, as illustrated in the example on the right. Other methods that can be used to address resonance issues include damping materials, dynamic vibration absorbers, and precision dynamic balancing. These methods are not really correcting the resonance problem, but rather minimizing its effects, and are usually only used when changing the stiffness or the mass is not practical. You have just completed Module 5, Diagnostics Part B. Please join us again for Module 6, Diagnostics Part C, which includes electrical, flow-related, and other problems. You can visit us at www.wilcoxon.com or contact us directly at 1-800-WILCOXON.